Thank you for inviting me to give this seminar. It's really a pleasure to talk about this science to a very broad audience in not only Earth's meteorological and climatological backgrounds, but with more broad planetary interest. So today I'm going to talk about stratospheric humidity and its role in Earth's climate change. Before I start, I'd like to acknowledge the people in my group, both the current members and the former members that have contributed to the results that I'm going to present today, including my student Gu, current postdoc Huang, and current postdoc Wang, and former PhD students and postdoc Zhipeng Qu, Yuwei Wan, and Yan Xia. Okay, we know that on many planets, as illustrated in this figure, do you see my cursor okay? Good.
Yes, yes.
And in many planet atmospheres, as shown here, the temperature stratification of the atmosphere is such that there's a stratosphere lying over a troposphere. In the troposphere, the temperature decreases with height. And in the stratosphere, the temperature increases with height. We know that the tropospheric temperature is mainly controlled by the radiative and convective processes on Earth. Between them, radiation, as shown by this thick black line, this is total radiation effect. A radiation effect leads to a net cooling of the troposphere. And this is because the atmosphere radiates thermal radiation, and this process make it lose energy and thus tend to cool. We have a relatively stable climate on Earth that doesn't constantly cool. That implies there is some warming mechanisms, and on Earth, this cooling by the radiation is compensated by the warming of convection. This is the latent heating associated with the vertical moisture transfer and the condensation driven by the convective circulation. So the temperature is understood to be in a radiative and convective equilibrium regime in the troposphere. In the stratosphere, it's mostly controlled by radiation only. You can see here the radiation heating rate is balanced. It's balanced between the cooling effect in the long wave, that's the thermal infrared radiation emitted by the Earth and atmosphere. This is a cooling effect as in the troposphere, but it's balanced by the absorption of the solar radiation by such species like ozone. So in contrast, the stratospheric temperature increases with height, and this is because stronger absorption of the solar radiation by ozone near the top of the stratosphere. So this boundary between the two atmospheric layers is called the tropopause. As discussed by this paper, it is usually located at a pressure level of about 0.1 bar. So that's 10% of the surface pressure on Earth. Okay. And this corresponds to an altitude about 20 kilometers or so on Earth. And because of the opposite temperature change directions in these two layers, decreasing here, increasing here, the tropopause is also the location where you see the minimum temperature. Okay. On the other hand, let's take a look at the humidity distribution. Among the many gas species in the Earth's atmosphere, water vapor is a peculiar one, in that its concentration varies by several orders of magnitudes from ground to the tropopause. So for this reason, the tropopause is also a hydropause. The boundary signifies different different mechanisms controlling the water vapor distribution in the stratosphere from that in the troposphere, which is a point I'd like to discuss next. If we put the humidity profile and the temperature profile together, as shown here in this figure, it becomes evident that the dramatic decrease of the humidity in the troposphere is due to the temperature control of the saturation, vapor pressure. This, in other words, is a thermodynamically controlled regime. We know that for every about 10-degree decrease of temperature, okay, the vapor pressure, the water vapor saturation pressure decreased by about a half. So given this relation, the about 100-degree decrease of temperature from the surface to the tropopause explains very well the humidity decrease over about 4 orders of magnitude from the surface to the tropopause. As the tropospheric humidity is controlled by the tropospheric temperature, our troposphere becomes moister as global warming happens. Shown here is the observed global mean surface air temperature accompanied by the moistening in the troposphere. In short, tropospheric moistening is observed and is well understood due to this thermodynamically controlled regime in the troposphere. And what about the stratosphere? Here you can see that the humidity is not local temperature controlled anymore. It doesn't decrease with, it doesn't increase with height as the temperature does. Okay, as water is transported from the surface and the troposphere to the stratosphere, it will be subject to the dehydration caused by the minimum temperature at the tropopause, this hydropause location. Okay, this then decouples the stratospheric temperature and the humidity. Then how does the stratospheric humidity change? On the observation side, some Earth observing satellites have suggested that the stratosphere is experiencing a moistening change. Okay, as indicated by this paper and based on these 2 satellite instruments, MLS and the SABRE. Okay, but there is no consensus about this. From the multiple satellite view of the stratospheric humidity record shown here, you can see that the instruments disagree about the moistening trend. Whether there is a trend or not, or how strong it is, the answer depends on which instrumentation group you talk to, or even just what version of the data you use. So people like Michaela Hagelin have led the efforts to homogenize the multi-satellite records. But it's fair to say that it is not conclusive from the current observations whether and how much the moistening there is in the stratosphere. What about the models? Very interestingly, most global climate models, this is what we commonly call GCMs, project strong stratospheric moistening during the global warming. As shown by this earlier paper of us, the moistening magnitude is quite significant. To read these plots, note that these are the zonally averaged water vapor concentration change plotted on the latitude and pressure or height space. Okay, in each of these cross sections is the result from one model, and the purple line here is the tropopause in each of these models. Okay, and the scale is base 2 logarithmism. So value 2 here means 4 times of the water vapor change compared to the unperturbed climate. So in this experiment of 4 times CO2 experiments, you could see that these models generally stimulate or project into the future a very strong moistening in the stratosphere, although the patterns and the magnitudes across these models could be quite different from one model to another. What about a newer version of the models? This paper led by Xia et al. This is an update from the previous paper, but based on the latest version of the GCMs. And these are the versions of the models that the latest IPCC report is based on. But you can see here the results are very consistent. There is significant moistening in the stratosphere, although the magnitude and the pattern differ among the models. A relevant note here is that these newer models now have higher model tops. So you could see that the model top pressure extend to 1 hectopascal or even lower. This means a very good coverage of the whole stratosphere. And besides that, many of these models have an interactive chemistry simulation in the models. This means that the stratosphere is much better represented, and the source and the sink turns of the water, as well as other substances, are better simulated. But nevertheless, the better resolution of the stratosphere doesn't make the models converge on the stratospheric water vapor change. Another very interesting note to make here is that the models not only project moistening while global warming happens, they're projecting the moistening rate is accelerating, as reported by this paper. For example, if you look at this model, this is the stratospheric water vapor amount, this global mean amount, plotted as a function of the surface air temperature. So you could see that at higher temperature, as global warming happens and global climate warms, at a higher temperature, the increased rate of the stratospheric water vapor increases with the temperature. Okay, so what implications may this have? For example, does it mean that the planet would lose water substance more easily to the space escape? This is a frontier question that we, as well as many others, are still investigating. But in this talk, my focus is on the Earth's climate, is on the Earth's global warming. Okay, why we're concerned about stratospheric water vapor in this context? A major reason is that stratospheric water vapor, as the tropospheric water vapor, it is a greenhouse gas. Okay, the water vapor molecules have multiple forms of energies and does have a very rich absorption spectrum. As you can see here across the infrared spectrum, both infrared and visible here. Okay, water vapor has probably the most abundant absorption lines across the whole spectrum. And it is the most important greenhouse gas in the Earth's atmosphere. If their abundance is increased, no matter whether it's in the stratosphere or in the troposphere, this may enhance the greenhouse effect of the Earth's atmosphere and thus potentially lead to greater warming of the Earth's surface. But this is exactly a problem, a concern people have hypothesized, as exemplified by a few papers that I listed here. Okay, these are all very highly cited papers. Many have tried to quantify the warming effect of the stratospheric water vapor, and they arrived at a number up to 0.3 watts per square meter per K. But their quantification is based on this fixed dynamic heating method, which I'm going to come back later. But first, let's try to appreciate this number, 0.3 watts per square meter per K. This number refers to the stratospheric water vapor's contribution to the overall climate feedback parameter. And this is a parameter that measures the climate sensitivity. As the global warming problem is fueled by the radiation energy, we can use this linearized equation to describe the climate change. This is based on the radiation energy balance of the Earth's climate system. At the top of the atmosphere, That is the boundary of the climate system. The net radiation needs to be balanced for the climate to be stable. So when the climate is subject to a forcing, for example, by the CO2 increase, this knocks off the balance, and the imbalance caused by the CO2 can be measured by this F term. This is the forcing term. So for the doubling CO2, that measures the radiative forcing we are experiencing right now during the global warming. This forcing magnitude is about 4 watts per square meter. And then warming will result, and to give out more thermal radiation energy to rebalance the radiation budget. Now, how much warming measured by delta T here is needed to offset the radiative forcing is then determined by this feedback parameter lambda. This measures the overall sensitivity of the climate system. And for the current Earth climate, this feedback parameter takes a value of about 1 watts per square meter per K. Okay, as summarized here from multiple model survey. This means that given a doubling CO2 forcing of 4 watts per square meter, the global temperature change would be about 4 degrees. This is a number often termed equilibrium climate sensitivity. So this overall number results from the contribution of many feedback mechanisms. Okay, and including first the Planck feedback, which lets the Earth give out more thermal radiation at a warmer temperature according to the Planck equation. And this is a fundamental cooling mechanism of the Earth. This mechanism is, however, offset by several major positive feedbacks, including water vapor, clouds, and surface albedo. Here, I'm not going to the details of these feedbacks, but just think about their magnitudes for now. Given the 1 watts per square meter per K overall feedback, then 0.1 watts per square meter per K feedback would be responsible to about 10% of the overall effect, or about 0.4 degree warming out of the 4K for the equilibrium climate sensitivity. Right? If the stratospheric water vapor feedback alone amounts to 0.3 watts per square meter per K, this will mean that over 1K of the warming can be attributed just to stratospheric water vapor. So in short, stratospheric moistening has been thought to be a highly impactful mechanism for surface warming. But then should we accept this theory? Should we take this argument to be correct? This could be counterintuitive if you think how small fraction the stratospheric air mass is in relevance to the total atmosphere air mass is only about 10%. Now I mentioned that the stratospheric water vapor is several orders of magnitudes lower in terms of abundance compared to the near surface values. This means the water vapor amount in the stratosphere amounts to a very small fraction of the total humidity in the Earth's atmosphere. But here it is argued that its radiative effect, its climate effect is disproportional to its total amount, its fractional amount, and thus this may be counterintuitive. So I think to verify this theory, we need to critically think about these important questions. First, do the climate models correctly simulate the stratospheric water vapor response? Secondly, does the moistening simulated indeed accounts for the significant warming in these models? So next, I'm going to try to address these two questions. To address the first question, whether the GCMs properly simulate the stratospheric water vapor response, we need to step back a little to think of what are the mechanisms controlling the stratospheric water vapor. The first mechanism which plays a dominant role is the Brewer-Dobson circulation, or BDC in short. This is a circulation pattern that ascends in the tropics and then carries substance forward in these pathways called shallow and deep branches. Given this circulation, it is easy to recognize that the temperature minimum in the tropical tropopause region is this minimum temperature illustrated here. This is based on data from a global reanalysis data set. Okay, and the colder temperature here then would play a strong controlling effect of the stratospheric water vapor, because the temperature would set the saturation vapor pressure. In other words, it would determine how much water can be let through this transportation channel. But this control of the tropopause temperature is well recognized and is evident by many interesting phenomena. One of them is the tape recorder effect. If you plot the temporal variation of the water vapor profiles as observed by the Earth satellite, for example here, by the MLS, and you could clearly see how both moist and dry anomalies indicated by these different colors, okay, originate at the tropopause and then propagate upwards. This is driven by the ascent of the Brewer-Dobson circulation. In fact, it is this kind of variability that provoked the earlier metallurgists, including Brewer and Dobson, to hypothesize the existence of this circulation pattern, which is now named after them. So for those of younger people who don't know what is a tape recorder, you should probably ask your parents about Walkman. I'm sure you'll all be shared with some fond memories of their youth. But anyways, this is a picture of them. Okay, this is a music recording and playing device. This has a magnet head like here. Okay, this registers sound signals on the tape as it passes through it. So in this analogy, the tropopause is like the registering heads, and the upward propagation of the signals is envisioned to be like being conveyed via tape. Okay. So what water vapor change may have been driven by the tropopause during global climate change? This is a hard question to answer based on observation. As I noted earlier, there's much discrepancy between the observation data sets, and this makes it difficult, if not impossible, to determine the long-term climate change of either stratospheric humidity or the tropopause temperature. Nevertheless, we can use shorter-term variabilities of these variables to detect the water vapor variational pattern associated with the tropopause temperature. If you correlate the variation of the stratospheric water vapor at different locations, as done here, with the tropical tropopause temperature, you will detect this positive pattern. This red area is where the tropopause temperature strongly controlled stratospheric humidity. But this pattern is evident from the observational analysis is not the same in these models. These models, they have quite different patterns of the moistening. So although the tropopause control, it is known to play an important role in modulating the stratospheric humidity, it is likely not the only factor or even a major factor that accounts for the stratospheric moistening simulated by these models. Then what else may be at play? But another mechanism I like to talk about here is convection, especially those really deep ones that develop very strong updrafts that penetrate the tropopause. as you can see here in these impressive pictures, there are these overshooting tops rising kilometer above the envelope clouds at the tropopause level. So besides the overshooting tops developed from this convection body, but still connect to them, sometimes we observe this very interesting jumping cirrus phenomenon, okay, which appears even above the overshooting tops. This signifies turbulence and breaking waves in this environment. And this phenomenon raises an important question. Is water substance, or how much of it is carried into the stratosphere by such overshooting convections? So realizing the potential importance of these convections, there has been much interest and many efforts, including those in my own group, to understand the magnitude of this transport mechanism and what processes control it. And here are some examples of our modeling studies. On the left here, this is a simulation using a Canadian numerical weather prediction model. By embedding domains of higher and higher resolutions over the North American domain, we are able to simulate the overshooting processes at 250-meter resolution in this innermost domain. But this set of simulations not only resolve the larger scale weather systems that generates the deep convections, but also the convective clouds and overshooting tops at very fine scales. This movie on the bottom here shows the water vapor concentration at the tropopause level. This is about 16 kilometer high. Okay, at the deep convection, as the deep convection develops, let me restart here. As this deep convection develop, you begin to notice these features that resemble the raindrops dropping onto the surface of a lake during a raining event. This difference, however, is that these raindrops are actually coming from below the surface. And these are the overshooting tops of deep convections that penetrate the tropopause and generate the gravity waves that propagate on the tropopause surface, just like the waves on a lake surface during the rain. And on the right, this is a cross-section view of the convection. So from this view, you can better observe the water vapor plumes being generated by the overshooting tops and the breaking waves, and then leave behind them the high concentration water plumes. So in this movie, we used the Lagrangian model to track the particles or air parcels of different properties to aid our analysis. So for example, distinguished in colors are the air parcels originating from different vertical levels. You can see that they are brought together. They're brought together by the turbulent wind fields near the overshooting top. Okay, at this moment, the overshooting happens, and all these particles are dragged towards the overshooting top while strong mixing happens. And after mixing, okay, and they settle back to different vertical altitudes, but carrying with them the moisture content to the stratosphere. So for example, this dark red stratospheric parcels carry with them this high concentration contents back to the stratosphere as indicated by this plume. Okay, so this allows us to do very detailed budget analysis of the water transport. So in our simulation using different model resolutions, we noticed an interesting phenomenon as observed by the others. Okay, this is a vertical transport of water vapor. It's increase in magnitude with the resolution of the simulation from from lower resolution to higher resolution, or from larger grid spacing to finer grid spacing, you could see that the vertical transport of mass and water amounts increases. This is not surprising because these transports, they are carried by these updrafts inside the convection tower. And these updrafts, they are, especially those strong ones, they are of very small spatial scales, and they are better resolved at a higher model resolution. But counterintuitive and to our surprise is the moistening results. In the finer resolution simulations, as indicated by this curve, we find the simulation can very well reproduce the humidity fields after the convection events in the upper troposphere and the lower stratosphere. In comparison, lower resolution models, they have an overestimation of the moistening. Okay. This is counterintuitive because we just mentioned that water vapor transport actually increases with the resolution, and it's those higher resolution that simulates more vapor transport. But through a budget analysis, we find this result is actually due to quantum physics. Most likely is due to the sublimation of ice. In the coarser resolution models, the ice becomes immediately vaporized because the grid box mean relative humidity is undersaturated if the model grid box doesn't resolve individual overshooting cells into individual updrafts, but only the grid box average the humidity. But in high resolution simulations, those high humidity cores of overshooting tops, they're protected from the warmer and the drier surrounding air. And this lets the ice largely sediment back to the troposphere, driven by the oscillating gravity waves. So the lesson we learned here is that the microphysics of cloud is important for quantifying the convective moistening. It is important for the climate models whose resolution is even worse, even lower than this coarser simulation we have used in this NWP model. So this something generally, this kind of transport and microphysical process is something generally not accounted for in the current climate models. So to this question, the answer is largely a question mark. And for the GCM simulated stratus water vapor moistening to be credible, more care needs to be paid to the moistening process. But the same thing or the same question can be made with regard to observations, which are not capable of observing the water vapor distribution right above and around the convective towers. This motivates the development of the better instrumentations. For example, this spatial heterodyne observation of water instruments, this show instruments that is being developed in Canada. So next, I'm going to change the gear a bit to address the other question, the other complementary question, that is, does the stratospheric moistening lead to surface warming? To answer this question, the best way we think is to conduct a mechanism denier experiments. We cannot do this with nature. So here we resort to a climate model. And in this work, we use a mechanism, we use a mainstream climate model, CESM, to conduct this mechanism denier experiment. So first we run a standard global warming simulation driven by the coupling of CO2. As shown here, this model simulates a significant warming, a global mean temperature increase to the CO2 forcing of about 8.4 watts per square meter. And this global mean temperature increase is studied at about 7.7 K. If we plug these numbers in this analysis equation, this means that the total feedback parameter is about 1.1 watts per square meter per K. So this matches the mean of most models. If the feedback strength of the stratospheric water vapor is as hypothesized to be 3.3 watts per square meter per K, then if we remove this from the total feedback parameter, then you can reapply this prediction equation for the data TS. Then you would expect a much weakened warming magnitude of about 6K. So this is the expectation if there were no stratospheric water vapor feedback effect. But when we do locking experiments using the same model, in this experiment, we lock the stratospheric water vapor concentration to the unperturbed climate. So by doing this, we effectively suppress the stratospheric feedback effect. This is why we call this a mechanism Denier experiment. But when we do this, we find the warming is indeed reduced, but the reduction magnitude is far less than the expected one. It is only about 0.2 K instead of more than 1 K. Okay, and this corresponds to order of magnitude less feedback parameter value of about 0.03 watts per square meter. So how can we reconcile this difference? Okay, to understand this, we need to review how the previous expectation is obtained. Okay, and this quantification includes both the direct radiation effect caused by the radiative agent, in this case, the stratospheric water vapor, which is termed instantaneous radiative forcing in this analysis framework. And this quantification, the previous quantification, also includes the indirect effect associated with the stratospheric water vapor as measured by the so-called fixed dynamic heating method. Now, without going into the detail, this is conceptually, this is to account for the cooling of the stratosphere driven by the increase of the thermal radiation to the space by the stratosphere. Okay, and this would add the amount of the radiation budget change due to this adjustment process. In theory, the troposphere may also adjust to the stratospheric water vapor change, but this was not included in this fixed dynamic heating assessment. So this neglect of the troposphere effect, adjustment effect, was justified by the conventional wisdom that the troposphere adjustment is usually insignificant. This is the case with the CO2 radiative forcing. As reviewed by this paper, okay, you can see that for the CO2 quadrupling forcing, okay, the bulk of the forcing is due to the instantaneous forcing and the stratospheric adjustment. The tropospheric adjustment, the contribution from this is very small compared to the other components. So this is justified for the CO2 forcing. But is this so? Is also the case for the stratospheric water vapor? But the answer from our locking experiment is no. This is a busy slide, so let me walk you through the results. So on the first column, this is the standard global warming experiments. And here you see when driven by the CO2 increase, the surface temperature is plotted as the zonal mean surface temperature increases, and increases especially in the Arctic. This is the so-called Arctic amplification of warming. But together with the surface warming, there's also warming in the troposphere. and the moistening in both troposphere and the stratosphere. The cloud amount also changed. This pattern signifies the high cloud is shifting to higher altitude. So you see this bipolar pattern change across the unperturbed climate's cloud location. Okay, and also there is sea ice melt, a strong melt of sea ice in the Arctic and the Southern Ocean region as a response to the warming. So the second column here shows the results from the locking experiments. When the stratospheric humidity change is suppressed, compared to this one, the stratospheric humidity is not changed by definition and by design of the experiment. Okay, most of the other variables maintain a similar pattern to the standard experiment if you compare these two columns. Okay, so in order to see the difference between the two, we show the difference between them on the third column. And this is the difference that you can attribute to the stratospheric water vapor difference, because this is the only difference in our prescription of the experiments. Okay, but this allows us to see better the change associated with the stratospheric water vapor. But noticeable difference here includes the stratospheric cooling. As I mentioned earlier, this is because the water vapor increase in the stratosphere increase the thermal radiation from the stratosphere to the space, and thus this mechanism cools the stratosphere. So this verifies that the stratospheric water vapor change is indeed associated with a strong stratospheric adjustment, as the previous study had concentrated on. But also interesting to find here is that the tropospheric change, there are many tropospheric changes associated with the stratospheric water vapor, including the warming of the tropospheric temperature here and the reduction of the clouds. Okay, and if we do a radiative analysis quantifying the radiative impact of these tropospheric processes, together with the stratospheric process. And then you realize that these tropospheric effects, they compensate the stratospheric effect, the initial warming effect of the stratospheric water vapor. And as a result, the overall warming effect is much mitigated from 0.3 watts per square meter per K to 0.03 watts per square meter per K in this experiment. So this is my last slide. Okay, in summary, we would like to note that the strong stratospheric moistening simulated by the GCMs, the global climate models, they put forward an interesting hypothesis, but this has yet to be, need to be observationally verified. And in terms of the surface warming effect, we find it is unlikely to be a significant factor. This is due to the coupling and the offsetting tropospheric effect that was not recognized before. Before I end this talk, I would like to add a disclaimer that the finding of the weak warming effect here of the stratospheric water vapor is based on one model in our study. So this is subject to uncertainty due to the model dependence. This needs to be verified to be more broadly studied with more models. And the surface warming, and on the other hand, the surface warming effect is not the only concern we have about the stratospheric water vapor in the climate change. For example, as reported in this newer paper by Xia et al., okay, there is evidence there are other aspects of the atmospheric circulation change that may be connected to the stratospheric water vapor change. Particularly in this paper, it is noted that there is a correlation between the widening of the Hadley circulation during global warming, which is a prominent set effect as studied by this paper and many other papers, and the stratospheric water vapor change. So much more unknown but important aspects of the stratospheric humidity I think still needs to be researched out. So I will end here, and this slides is a listing of the related papers about the talk today, and I would be happy to take any questions if we have any.